This talk, I will discuss some topological phenomena that emerges in the Moiré pattern of van der Waals heterostructures. So these van der Waals heterostructures are, oops. Okay. So these van der Waals heterostructures are formed by stacking the monolayer 2D crystals. Recently emerged transition metal dicalcogenic families, which are 2D semiconductors. So first I will give a quick overview of the properties of the building block, mainly focused on the physics associated with the fact that the carriers are located at the valleys, at the corners of the brilliant zone. So I will first introduce some valley phenomena from our earlier work. And when you stack different building blocks on top of each other, naturally they will form Moiré pattern because the lattice mismatch and the inevitable misalignment between the crystalline axes. Because the carriers are now localized at the valleys instead of the usual gamma point, we show that the way that interlayer coupling happens is controlled by the stacking. So in the Moiré pattern, you have different interlayer atomic registry at a different place. And the properties, depending on this stacking, will lead to laterally modulated properties. So I will discuss two systems. One is when you have a type 2 heterojunction between the layers with a finite gap. So in that case, I will discuss the quasi-particle of excitons, bonded electron hole pair, and we have a spin-orbit coupled superlattice of excitons. And you can also use electric field to tune this band gap to the so-called type 3 heterojunction. In that case, you have band inversions, and these band inversions are also controlled by the stacking order, which then leads to a tunable superstructure of a topological insulator. So the building block is the family of two-dimensional transition metal dicalconite, where the metal can be molybdenum or tungsten, calcium can be sulfur, selenium, or telluride. They have a bulk crystal, which is of the layered structure. Monolayer is a 2D hexagonal lattice and weakly bonded to each other by the van der Waals force. So on the two sides, you have either metal or two calcium. When you think down from bulk to monolayer, there are two essential changes. One is the inversion symmetry is broken in the monolayer. The other is bulk is an indirect band gap semiconductor, but monolayer becomes a direct band gap one. So if you look at the band structure, both the conduction band and the valence band has the edge at the corners, K. So for the 6 corners, only 2 of them are inequivalent, which are called K and minus K. So this effectively give carriers additional internal degree of freedom, which are called valley pseudospin. In our early work together with Chen Liu and Di Xiao, we find that in these 2D hexagonal crystals, if you break the inversion symmetry, then the two valleys can acquire opposite barrier curvature, optical selection rule, etc. So this allows you to address the two valleys separately using external field, making possible the use of this valley pseudospin in future electronics. And microscopically, this valley physics arises from the fact that the band edge carriers are described by the massive Dirac fermion model. So if we look at this band edge, they are mainly from the two d orbitals of the transition metal atom. So conduction band is from the m equal to 0 d orbital, and this is a linear combination of these two d orbitals, which have the magnetic quantum number either of +2 or -2. Based on these two orbitals, you can construct a minimum Kp Hamiltonian. It turns out to be the massive Dirac fermion model, but with it's just like the graphene, but just with additional mass term. We know that this massive Dirac fermion is associated with a finite barrier curvature, but because now you have two valleys and they are time reverse of each other, so the barrier curvature at the two corners must have opposite sign. So then if you consider electron motion in an in-plane electric field, then a carrier from the two valleys will have opposite transverse velocity. So that's an analog of the spin Hall effect, which you can not call it a valley Hall effect. So this is some property that we earlier in our earlier work together with Chen Liu and Di Xiao based on the graphene model. But now since this transition metal dicalconide have the same KP Hamiltonian, so you expect the same set of things. Also, this valley optical selection rule. So the interband transition at K and minus K couple only to circular polarized light, but with opposite helicity. So now you can use this selection rule to selectively excite electron hole pair, either in K or minus K. And in this transition metal, we have a very strong spin-orbit coupling. That's what distinguished from the graphene model. This spin-orbit coupling has to take this symmetry-dictated form. It has to be in the Z direction because of mirror symmetry in the crystal. And the two valleys are time reverse of each other, so that means the spin splitting has opposite sign. So this effectively locks the spin index to the valley index. For example, at the valence band edge, where you have the really large spin orbit splitting, you only find the spin down carriers in K and a spin up carrier in minus K. So in another word, when I talk about valley in this particular material, you can also think about the spin. You only get one spin species per in each valley. And based on this optical selection rule, we can use light to manipulate the valley pseudospin of electron hole pair. So this is a block sphere to represent the valley degree of freedom of electron hole pair. So if it sits in the K valley, that's the north pole, and the minus K valley, it's a south pole. And other point on the surface is a linear superposition. So you can now use left-handed polarized light to access the north pole and the right-handed polarized light to access the south pole. But then other points, as I mentioned, it's a linear superposition. And linear polarized photon is a superposition of left and right polarized ones. So you can also use linear polarized ones to access those superposition of different valley states. And also to mention, there is a very strong Coulomb interaction in these 2D semiconductors. So that will bond the electron hole pair into the hydrogen-like bond state known as excitons. So in this system, excitons also have interesting properties because of this strong binding. So you can either have the neutral electron hole pair or charge the electron hole pair when they capture additional hole or electron. And for this hydrogen-like bond state, in this material, it has a binding energy that is about more than one order stronger than in that in gallium arsenide, and the Bohr radius is really small. That means electron and the hole has a much larger opportunity to get on top of each other, which leads to strong exchange interaction. So what this exchange interaction does is it scatter electron in one valley into the valence band. At the same time, valence band electron is scattered to the conduction band. So if you put this in the context of exciton, that's like annihilating an exciton in the K valley, but create one in the minus K valley. So this exchange interaction acts as a transverse coupling between the two valley configurations. And that coupling depends on the center of mass momentum of exciton. So, and the rotational symmetry of the crystal determines that this coupling is zero at the zero momentum, and there is a chirality of 2 represented by this phase factor. So if we now look at the exciton dispersion in this transition metal dicalconide, it no longer has the regular parabolic dispersion, but instead it is split into 2 branches. One branch, you have a rather steep linear dispersion conically touching another parabolic branch. And they have a opposite pseudospin winding of a chirality of 2. So if you focus on light cone, that's the region where exciton can be coupled to photon and become bright. That's what it looks like. Sharp cone and rather flat, a very massive one, and a massless branch. And using strain, you can further split this touching point of chirality 2 into two touching point of chirality 1 each. And besides, when you look at those charged species of excitons, when you have additional electron bonded to this electron hole pair, there is an exchange interaction of this electron hole pair with this extra carrier, and that one will acting together with the electron hole pair exchange between them, they lead to a gapped Dirac spectrum once again. So in this gapped Dirac spectrum, you would have a large barrier curvature distribution. And this charged species of exciton will move in the electric field. So if you optically excite a doped system to inject trions, you would have two species, one picking up a positive and then the other picking up a negative anomalous velocity and moving to the edge. And they have opposite spin and emission helicity for the photon. And these valley physics of the monolayers, many of them have already been observed experimentally. So the optical selection rule has now become a standard mechanism to access the valley degree of freedom in these semiconductors. And the valley Hall effect has also been observed combining the with the valley optical selection rule. And recently in graphene, it's also measured in purely electric measurement through the non-local transport. So that is a brief overview of the monolayer properties. And the key is that electron hole are now described by massive Dirac fermions. And also excitons, they have a Dirac spectrum for a separate reason, which is due to the Coulomb interaction from the electron hole constituents. So now I will go to the van der Waals heterostructures. That is when you stack different monolayers on top of each other. And the interesting thing arises when you have interlayer coupling of these massive Dirac cones of the carriers. So for this dicalconide family, when you stack different compounds on top of each other, they usually have this so-called type 2 band alignment. So this red band are from upper layer, blue are from lower layer. So the conduction band are mostly contributed by one layer and the valence band from the other layer. So in this case, the excitons would have the so-called interlayer configuration because electron hole would have low energy in separate layers. And those interlayer excitons have been found with appealing properties with very long lifetime, but still bright so that you can observe them using photoluminescence and very long lifetime because the major mechanism for the valley depolarization has been quenched in this interlayer configuration. So that's one thing that I want to discuss. And the other thing is when you use the electric field, which can tune the relative band alignment into the so-called inverted type 2 or type 3 region where you have broken gap. And in this case, we can look into the band inversion and see what is the Moiré effect on these inversions. So that's the two things we will discuss. Let me focus first on the interlayer excitons in the Moiré, which turns out to have artificial honeycomb lattice with a very strong spin-orbit coupling due to the Moiré effect. And the key to this Moiré effect is interlayer registry matters in the interlayer coupling. And this is largely due to the fact that you have carriers located at valleys instead of the gamma point. So none of these things will emerge if the band edge are actually in the gamma point. So we can first look at the optical properties to see why valley matters. So the optical transition selection rule, you can derive it based on the threefold rotational symmetry. So under rotation, the valence band and the conduction band can transform differently, and it's their difference determines whether it can couple to a sigma plus or sigma minus polarized light. But in considering how this state transform under the C3 rotation, you have to notice the fact that the block functions are now at the corners of the brilliant zone, so that you have this additional phase factor in addition to the rotation behavior of these Wang Yao orbitals. So this phase factor if you project them onto the lattice side, you can clearly see that the factor it contributes on the rotation would be determined on the choice of rotation center. So this is the same lattice with the same projection of phase factors. But if the rotation center is here, then the transformation is like angular momentum state over L equal to 1. But if you choose a different rotation center, it's like an angular momentum state of the opposite angular quantum number. And if you choose the rotation center in a third way, then you have no phase winding at all. So this factor it has this feature of dependence on the choice of rotation center. But in a monolayer, because the electron and the hole are sitting on the same lattice, so which one you choose as a rotation center does not matter because they change in the same way. So therefore, in monolayer, you have a definite selection rule, which is only depending on whether the electron hole pair is at k value or at the minus k value. But then when you go to heterobilayer, with the electron and the hole separated into two lattices, then how these two lattices stack on top of each other matters, because that determines the choice of rotation center in the electron layer and in the hole layer. So for example, in this stacking order, if you look at that C3 eigenvalue, it would lead to the conclusion that electron hole pair, when they annihilate, it emit a right-handed polarized light. But if you stack the electron hole lattice differently, the same electron hole pair with the same valley configuration would lead to a photon of opposite helicity. And in this stacking, the conclusion is that the electron hole pair cannot recombine because it is not allowed by the angular momentum conservation. So, and then in the Moiré pattern, we know that different locals of the Moiré would correspond to different local stacking order. And this symmetry analysis is implying that the optical properties of the exciton would vary spatially because of this atomic registry variation. So this is a picture we will have for the exciton light coupling in the Moiré pattern. So this is the brightness of the exciton. At some regions, you have bright couplings, but it is a photon emission is completely forbidden at this point, which is based on the symmetry analysis in the previous slide. And the two regions here, they also correspond to different photon helicity for the same valley species. And generally, at a general point away from these three high symmetry stacking orders, you would expect elliptically polarized photon emission with valley contrasted helicity. So the time reversal symmetry is still there. So the brief message here is in the Moiré pattern, you have this local-to-local variation of atomic registry, and that leads to different form of interlayer coupling, which laterally modulate the optical properties. But in the Moiré pattern, you also expect the modulation of other physical quantities, like the band gap and the topographic height, the separation between the two layers. So these quantities will also manifest in the property of interlayer excitons. So the electron hole pair, their energy is directly given by this band gap. So this band gap variation, so this is a plot of the local band gap if you move along this supercell, Moiré supercell along the diagonal line. So the different local gap leads to different energy of the electron hole pair at a different spatial point. So this is the potential energy that the exciton would feel in such a Moiré pattern. But then this, in the real space, this interlayer exciton is an electrical dipole, permanent electric dipole in the z direction. So this will also couple to the perpendicular electric field. And because the interlayer separation are different, then the coupling strength to the field differs from place to place. So that means if you apply an electric field interlayer bias, you can also tune this energy profile from this triangular lattice to the other triangular lattice with minimum shifted from this A point to the B point. And this middle configuration is what we thought to be most interesting, where the energy of these A and B regions become equal, and that gives rise to a honeycomb lattice. And this honeycomb lattice, it's very different from the graphene model. So as I just mentioned, the two regions, A and B sites, they correspond to different interlayer stacking, and one coupled to left-handed polarized photon and the other coupled to right-handed polarized photon for a particular value of spin species. That means the exciton have a distinct rotational symmetry at these two local minimum. And because of this, the hopping between these sites must carry a complex phase. So if you look at the nearest neighbor hopping, that's a phase factor for different from these three hopping, and also for the third nearest neighbor hopping. And the next nearest neighbor also has this complex phase. Actually, we can have this figure out these general hopping phases in such a superlattice because of this Moiré-induced local registry difference. So this is the amplitude, and the phase factor would be determined by the separation of the electron and the hole band edge in the momentum space. So in the Moiré pattern, because of the twisting or because of lattice mismatch, so the electron layer and the hole layer, the band edge are at the corner. So then this twisting or this lattice mismatch would shift the electron band edge away from this hole band edge. And it is this separation that determines how the phase pattern changes when exciton hops in such a lattice. And the time reversal symmetry is still there. So this photon helicity refers to one spin species. If you look at its time reversal counterpart, then this complex hopping phases have the opposite sign. So then you have a spin-dependent complex hopping lattice. And if we look at the spectrum of the excitons in such a lattice, the blue one refers to spin-up excitons, and the brown one refers to the spin-down one. And interestingly, we find several conical touching points. This is a four-fold degenerate point, a Dirac node, and these two are two-fold degenerate for one spin up and one spin down species. And these three Dirac or wire point is actually due to the fact that I just explained. You have this complex hopping, and that's like a momentum space shift of the spectrum. So if we only consider this amplitude part, then you have a honeycomb lattice. The honeycomb lattice have this graphene-like spectrum with two Dirac cones, originally at the K and minus K corners. But because of this complex hopping phase, the entire spectrum is shifted in the momentum space. So the two Dirac cones are now shifted by this amount, and one is now goes to this gamma point, and the other shift from one corner to the other. So that's for the spin-up exciton, and the spin-down exciton has the opposite momentum space shift. So as a result, at the gamma point, you have this spin degeneracy. So it's this four-fold degenerate point. And then you have a spin-up Dirac cone at the K corner and a spin-down Dirac cone at a minus K corner. So that's what you have in this spin-orbit coupled exciton superlattice. And such a spectrum can be described using a tight binding model. The low energy section can be described using a tight binding model counting up to the third nearest neighbor hopping. And you can also find this branch of topological edge states that connect the two wire nodes of each spin species. But because of this shift, the edge states also get separated in the momentum space. So this exciton spectrum can get gapped by applying interlayer bias. And then this edge channel can be separately tuned by a potential that is localized on edge from the flat one eventually to a gapless one that looks to be chiral in this gap. So that's what you would expect for excitons in the Moiré pattern. Next, I want to discuss the other situation when you have a electric field to tune the band gap into the type 3 region so that we can look into the band inversion. So if you apply this field, then the two blue bands will be shifted relative to the red ones, and they can this gap can close, and when they open again due to the hybridization, two things can happen. One is the trivial one, you have this avoided band crossing, where the interlayer coupling always leaves a finite band gap there. So in this case, nothing interesting will happen. But the other situation is the gap closes once, and when they reopen, you get a topological phase transition where the gapless helical modes emerge in this hybridization gap. And which of these two cases will happen depends on how the interlayer coupling between the two Dirac cones. So now we have two bands from one layer each, so a total of 4 bands. So altogether, there could be 4 interlayer hopping channels between these two and with that two. And they have very different characters in determining how these two energetically overlapping Dirac cones hybridize. For example, if you can go from here and then undergo intralayer interband coupling, so that will lead to this form of hybridization, or there is a direct hybridization between the two if this channel dominate. But then these different pathways have different topological characters. If interlayer interband transition is involved, remember this is the one that in the massive Dirac cone model, massive Dirac fermion model, where the coupling has a chiral dependence on the momentum away from this energy minimum. So that's the Q minus or Q plus term here. So once such a term is involved, then there will be a topological phase transition if these two hybridize and open hybridization gap. So this channel, if that one dominates, it would lead to a spin Hall conductivity of 1, and the other dominating channel would also lead to a spin Hall conductivity finite to it's -1. But these two channels, its overall effect is non-chiral, so this would give rise to a trivial case. But then which of these 4 channels dominate depend on the interlayer stacking once again. Because the hopping matrix element has also to be dictated by the C3 rotational symmetry of the band edge block functions. To have a finite hopping, the two wave functions in the 2 layer must have the same transformation. But as we mentioned, because these wave functions are now located at the valley, so you have to consider these phase factors corresponding to the momentum at the Brillouin corners. And that depends on the choice of the rotation center. And the fact that you can stack the 2 layers differently means that you would have different interlayer coupling channels. So now we can look at, for example, consider this particular case, this stacking. In that case, the metal atom of the upper layer stack on top of the calcium atom of the lower layer. So if you want to choose a rotation center to be the metal atom on the top layer, then it would be the calcium side of the lower layer. So then we have this table that gives the C3 eigenvalue of the rotation behavior of electrons in upper layer and the hole in lower layer. So we have chosen the metal to be side to be the rotation center and the calcium side to be the rotation center in the lower layer. So it's this vertical dashed line. But then the requirement that the 2 wave functions has the same C3 eigenvalue would forbid these 3 interlayer hopping channels. So the only possible interlayer hopping channel is between the valence band in the upper layer and the valence band in the lower layer, where you have the same eigenvalue under this choice. So that means under this particular stacking, So under this particular stacking, high symmetry stacking, we only have this interlayer hybridization term, and that would dictate that this heterobilayer would be a quantum spin Hall insulator if you go to the inverted regime where the two Dirac-Cohns overlap. And by similar argument, we can show that the other two type of high symmetry stacking that preserve the C3 rotational symmetry, this would correspond to a quantum spin Hall effect as well, but with opposite conductance. And this configuration corresponds to these two trivial channels, and it will remain as a normal insulator. So this is a table that summarizes the all 6 high symmetry stacking orders possible in these hexagonal lattices. And they correspond to different quantum spin Hall conductance. If we go to a general stacking order between the two layers, that is characterized by in-plane separation between the two, for example, the two metal atom side, one in lower layer, one in upper layer. Right? So in general, you can have a translation between the layers. That a translation will give you a different configuration. So this corresponds to metal on metal or metal on calcium, but in general, you can also have a general in-plane displacement between the two. And we can use this phase space to where each point corresponds to an in-plane translation vector and describe the topological phase transition in such a space. The high symmetry point that we have just discussed correspond to these 3 points. And the 2 of them are topological insulator with different quantum spin Hall conductance. And this one is a trivial insulator. And then at general, we can find that at the general translation, we have this phase diagram where the 2 topological regions, finite topological regions, surrounded by topological trivial regions, which I in blue color. And this is how the phase transition happens as a function of the band gap. This is, or in other words, that's an electric field, which tune the band gap, close it, and then reopen it, go to the hybridization region. So when it closes, the 2 topological points start to emerge at this high symmetry configuration. And as the inversion gets deeper and deeper, you have the finite areas of topological insulators emerge in this phase space. So, so each vertical line is a fixed configuration on a different electric field. So that's a trivial transition. That's a trivial avoided crossing. And then this is along this line, you get a topological phase transition as a function of electric field. So this is what happened in a lattice matched bilayer, but you use as interlayer translation or interlayer registry as a parameter. But then in the Moiré pattern, as we have previously discussed, you have these local regions. If you zoom in, if the Moiré period is much larger compared to the lattice constant, then in these local regions, you hardly find any difference from a lattice matched bilayer. But in the over long range, when you go from one local to the other, you have this change of interlayer stacking from one kind to the other. And if the electronic properties, local electronic properties, can be approximated by the corresponding lattice matched bilayer, then based on our previous discussion, we know that these 2 configurations would dictate topological insulating regions when you have inverted band gap. And this configuration must correspond to a trivial insulator. So the topological phase diagram for lattice matched bilayer can now be mapped into a real space phase separation pattern in the Moiré pattern. So you get topological insulator regions surrounded by normal insulator regions where the helical edge modes flow on the boundary within the hybridization gap. So and moreover, in the Moiré pattern, we know that it is fully determined by the lattice mismatch between the 2 layers. So if you apply strain to one layer, you can modulate this Moiré pattern from this 2-dimensional Moiré pattern eventually to this 1-dimensional Moiré pattern. So if the local approximation holds, then you would expect the tunable Moiré topological insulator superstructure from 2D arrays of nanodots eventually to a 1D arrays of a nanostripe. And for this one-dimensional case, it is easier to do a real space calculation of the Moiré pattern to look into the helical states on the boundary to verify whether the local approximation is good or not. So this is what we have done, a calculation for the one-dimensional Moiré pattern based on a tight binding model. And indeed, you find the helical modes flowing in the band gap, hybridization band gap when you invert go to the type 3 region. And the location and the chirality of these helical modes are exactly predicted by the local approximations. If you change the lattice mismatch, these helical modes, they have a finite width. So when the Moiré pattern becomes small enough, that they can couple due to a finite size effect, and then the spectrum becomes fully gapped once again. So one possible use of this electrically tunable and strain controllable topological phase transition is it may function as a principle for the transistor. So unlike using gate to tune the doping in the conducting carrier density in the conducting channel, here what the electric field can do is to so in the off state in the gap you have nothing. But once this topological phase transition occurs when you change the electric field and go to the inverted regime, then states will appear in this hybridization gap. And unlike the conventional, unlike the crystal topological insulator, where you only find the helical modes on the edge, now you can have a densely packed helical modes, which are now determined in the bulk, determined by the phase boundary of the, and this length separation between these neighboring channels are fully controlled by the strain that defines the Moiré pattern. So that will lead to a much larger conductivity compared to the single channel on the edge. So with this, I would like to summarize the talk. The properties that I discussed, one important origin is you have carriers which are massive Dirac cones localized on the brilliance corners. So this is very important. The fact that the band edge are at the valleys leads to the stacking control the interlayer coupling. And then in the Moiré pattern formed naturally when you have van der Waals heterostructures, that stacking controlled interlayer coupling leads to lateral modulation of optical properties as well as topological properties. You can have a spin-orbit coupled Exciton lattice and also programmable superstructure of a topological insulator. So at last, I want to thank the people that I worked together with on this subject. My group members, in particular, Dr. Yu Hongyi and Dr. Qingjun Tong. So Hongyi did the Exciton work, and Qingjun did the topological insulator part mostly. And also, I would like to thank my long-term collaborator, Xiaodong Xu. So he's leading the experimental group at the University of Washington, and this is part of the long-term effort that we try to understand the optoelectronic properties of these 2D semiconductors at their heterostructures together. And also, Guibin Liu, my former postdoc, and Wang Yao at the Nanyang University, they have provided support on first principle calculations. And thank you for your attention.
Thank you very much. So, questions or comments? You're very quiet this afternoon. Yes?
How do you expect so in your Exciton, second part of it,
Mm-hmm.
right? So how you thank you. So how you expect to maintain the excitons in practice in an experiment? So do you have in mind you have a light pulse, and then within the time it takes for recombination, you would see this contribution to the normal spin Hall, or you have continuous excitation? So how would that work?
Okay, the key is these excitons have very long lifetime. So unlike the excitons in the monolayer, they can survive more than microsecond or even longer. That's already observed in experiments from the photoluminescence of these interlayer excitons from my collaborators group. And besides that long population lifetime, you also have this long valley lifetime over a few tenths nanosecond. So this gives you a large window to do whatever manipulation, either for the valley degree of freedom or other things. So you can do the optical injection, excite. The best way is perhaps for optical injection is to excite at the resonance of interlayer exciton. That's where you get the most absorption. And then there will be a very fast interlayer charge transfer process. It's a sub-picosecond. So then this interlayer exciton will just immediately become interlayer exciton. And then they will relax the excess energy and go to those energy minimum in the superlattice. And also you can do the electrical injection, right? So you inject electron and holes in separate layers. So they form a like p-n junction, a vertical p-n junction.
Other question, Herb?
So I suppose that you have currents of these excitons in the superlattice, right? The superlattice effect, yeah, the superlattice that you showed of the excitons. Is there any way to observe this current of the excitons? Is there charge neutral?
I guess one way is to look at the counterflow geometry, right? Because the electron holes sit in different layer. So if you can make electrode contact to different layer, then you can do this counterflow experiment. That's a way to look at the superfluidity of the exciton condensation. Okay. But the other ways are optical measurement, because these are actually emitting light. Although they have very long lifetime, they still emit light. So you can do, but you don't detect a current, but right. That's other properties you can look into. Yeah.
Other question here, I think in the...
Right. Thank you for this interesting lectures, talk. I was wondering for your Moiré pattern, whether it's possible for the two topological insulator region to be brought together, yeah. And what happened?
So if, I think, so the thing is, if you have this 2D Moiré pattern, the real space pattern is always mapping to the phase space diagram in the. But if you use strain, then you can see it's like stretching the Moiré pattern in one direction very drastically. But still, these two topological regions remain separated. And the only way for them to talk to each other is when you have the Moiré period small enough. If the Moiré period, this separation is smaller than the width of the helical states, then these two boundaries can talk to each other through the finite size effect. In that case, the spectrum get gapped. But so far, I'm not aware of any possibility to merge two topological regions into one region. It's only, they talk to each other through finite, because the separation is, spatial separation is not big enough. That's the only way they talk.
There was another question in the front.
Just for context, for the non-expert, could you contrast this system with any similar effects that you might get in stacked graphene sheets that are rotated with respect to one another?
So graphene, for example, on boronitride, is that the system you are referring to? Well, they are also the Moiré pattern, but graphene is initially they don't have a gap, but when they stack on boronitride, they also have this Moiré modulated properties. So for example, in one region, the gap it acquired can have a positive sign. In the other region, it can have a negative sign. So that will also lead to very interesting topological phenomena. Because if you have opposite mass regions, then you also expect some helical modes, but that's not spin helical, because in graphene, spin is not relevant. It could be chiral states with different chirality in valley k and minus k. But still, it's a helical network. And people have a look into that in the context of graphene. Yeah.
Other question or comment? There is one here on the nearly last row. No, just behind. Yeah, you.
I'm sorry, can you speak louder? Right. Oh. Yeah, that's an interesting question. So far, we have not considered the Coulomb effects in this band inversion. But if you take that into account, then you would go to a regime. And also, external insulator is fully due to the Coulomb interaction, not interlayer hopping. So that's actually a different regime compared to what I look at. Now, this case is a interlayer, single particle interlayer hopping that leads to this. But for external insulator, you probably want to have the two layer more separated, so there's no single particle hopping, but then the Coulomb interaction dominates the inversion. So that would be the external insulator.
And one final question in the front.
Hi. I may not have fully catch every detail in the talk, but it is very interesting to me, and I want to ask. You show the graph you showed us that there is a phase diagrams. So the critical point for this phase transition, is it only related? Is only dependent on the interlayer interaction, or does the spin-orbit coupling effects also can influence the phase transition?
Oh, I think in general, yes. Of course, spin-orbit coupling matters in opening the band gap. But in this transition metal dichedron, spin-orbit coupling comes in a very simple form. It's only splitting in the z direction with opposite sign at the two valley. So then we can completely forget about spin-orbit coupling. You just get a spin-up Dirac cone in k and a spin-down Dirac cone in minus k. That's all. And then the remaining would be determined by the interlayer hopping. How that depends on the interlayer stacking. Yeah, but in graphene, if you induce some spin-orbit coupling, which can take different form from one local to the other, that could be another causes leading to this phase separation in the real space.